Hello, good morning. We're here today to talk about advanced press applications made easy. My name is Glenn Nausley. I'm the president of Promess Incorporated. I did spend 25 years in application engineering with Promess. My co-host today, my partner here is John Lytle. He's been application engineer with Promess for about 20 years, and he currently heads up our application department. Today's event, we're basically going to be, this is a second part to one that was done earlier.
Yeah, the one that was done earlier, we focused more on kind of basic press fit applications and how to analyze those and determine whether your parts are good or bad. So one was press to a force, which basically means we're using the integrated load cell in our servo press to control through a force. So like bearing pressing, anything that has a press fit that presses to a shoulder, generally you're going to use a press to force type program to do that. The other one is press to a position. Now keep in mind these are all the basic applications, and as Glenn said earlier, we're going to focus more on the advanced as we get into this webinar. But press to a position, where basically we're taking just the feedback from the servo motor, an encoder or resolver, and we're pressing to whatever we program it to press to. Yes. So as that press ram moves down and I tell it to go to 100 millimeters, it's going to press the parts together to 100 millimeters and call that done. Of course, we have all the analysis around that with the load cell and the graphing functions that our systems have. Number 3 is press to a probe. That's where you can have a little more precise pressing, where you can get down to the micron level. And some of the stuff we talk about today is going to talk about that. And then number 4 is press to a touch point, and then to a position. So what that means is we can generally come down, use the force sensor, locate where the part's at by feeling it with the force. And then from there, we can press a relative amount. So that generally takes in stack ups and different things like that in the assembly, and gets rid of them and allows you to press relative to that point. So that's kind of what we covered last time, and we had 2 other application engineers doing that.
Yeah, these functions too, is particularly 1, 2, and 4, can all be done with the internal sensing in the press, right, which is the position sensing generally off the motor, encoder on the motor, and the load cell. And this is a 3 kilonewton Promess press. This is a real production press, one of our smaller models. We make presses that are as big as we are. They go up to hundreds of thousands of pounds, but this is one of the smaller guys.
Right, and it's important to note too, when we're pressing these components together in press fit applications, a lot of times the pass or fail criteria is based off signature analysis. And what that means is graph. So we can remember as a part goes together, we can put limits around the graph and things like that, and that can determine whether the part is an acceptable part or not. Where today what we're going to talk about is a little more of an advanced type methods for pressing to a function or making and then measuring, or measuring and making. And the difference there is it's less focused on the graphing analysis, and it's more focused on making the part function the way you need it to function, and also to position parts to a part dimension so that it works properly in its application.
Okay. Oh, you take that.
Okay.
That's one of the reasons I brought John along. He's younger, stronger than I am, so he can carry the press around.
That would be a problem for me.
Yeah. So today what we're going to be talking about, as John mentioned, are more advanced applications. Now, advanced in the technology and the technique, not advanced in the complexity. These are actually very simple applications to do in today's world with today's technology with servo mechanical presses. The difference in these are that they take external. You have to have some either external sensors, external actuators. There's 2 of them we will be focusing on. One is we call it measure and make. It's dimensional cloning. An example that we're going to be talking about is bushings into a control arm, where we're actually measuring with measuring probes, gauging position. The second option, or the second technique, is what we call make to a function. Very, very similar. With the measure and make, you have to add external sensors, primarily probes, measuring probes. So you have external data, which is helping you control the motion of the press. With make to a function, you have external sensors also, but generally it's not dimensional sensors. It's other types of sensors measuring the function of the process.
Right. A lot of times it's another axis of motion used to be able to crimp, roll over, do things like that while actuating the assembly to make sure that it has the right fit and feel. So it's similar to make, measure, and make, but it's actually making it to a function, meaning that it functions properly and functions exactly the same from one to another.
Each time, yep. And so the first example is a control arm pressing the bushings into a control arm. This drawing here shows the critical dimension. First is bushing A has to be pressed to a dimension. We're going to focus in our explanation on the relative distance or relative placement of these bushings for dimension B. If you think like a normal control arm, these bushings being pressed in, the critical dimension is from the face of this pin to the face of this pin. That's where it interfaces with the vehicle. This slides over the frame of the vehicle. Bolts are put in here, and they're and it's attached to the vehicle that way. If this dimension is too large, then it's sloppy. If it's too tight, it won't fit in. And this is a pretty easy part to make on print, but there are some complications.
Yeah, one thing I'll point out is that generally it takes about 8,000 pounds of force or more to press these bushings in. So you can see how a typical control arm is. As you press on here, you're deflecting this portion of the part, making it real hard to keep this span, the span they need to hold. So that's why they call out these part dimensions. So just pressing to a position like I talked about earlier is not going to work. You're not going to get acceptable results. They're going to go to put this in the car. It's not going to fit. And surprisingly enough, these applications, they hold these tolerances that Glenn just mentioned here to a pretty tight tolerance, like less than a half a micron in some, or less than half of a millimeter in some cases.
And if you look at the bushing, this is a typical bushing. We have a few different models here, a few different types, but they all have the same issue. As you're pressing these bushings into the control arm, so as I'm pressing this bushing into the control arm, I'm pressing on this outer can. So the press can be perfect and press that outer can to the same place on every single control arm which is manufactured. The problem is nobody cares where that outer can's at. The important dimension is off this face of this pin here, and the tolerance on these bushings are all over the place. These pins are maybe plus or minus 2 millimeters, and then you're pressing two of them, so you have a stack up tolerance of plus or minus 4 millimeters, and you're trying to press them to within a half of a millimeter.
Right.
So what we do, or the solution for that, is this measure and make technique, where the machine fixturing has probes built into it and is literally gauging, measuring this span as the parts are being assembled.
Right. So what makes it simple from our aspect is that we can simply take these probes into our system, and we have canned routines that are parameterized. So you're literally just entering in values. The system calculates what needs to happen, and then it adjusts. And it's a servo system, so it's very precise. Measuring probes have accuracies of a micron. So we can then take out the deflection, measure the point Glenn referenced there. So deflection's gone, force is gone out of that equation. Variations in this bushing are now taken into consideration, and these parts get pressed consistently from one to the other.
Yeah, so now when you're pressing these bushings in with the presses, you're pressing it in, and you press until the probe says that this dimension is correct. You're not pressing the can to a position, but you're pressing the critical surface to
Right.
the position. What's the most important thing in an application like this?
Well, the most important thing I think is that the machine's designed to be a gauge and not an assembly machine like typical people think about it.
Yeah.
So basically designing your fixturing is the hard part. Designing that so that you're measuring the right surfaces and that it measures it the same every time.
Yeah, it's the old cliche, garbage in, garbage out. The key thing to being successful in an application like this, and where we've seen the difficulty, the controlling of the position is easy. All of this is an easy operation if you're getting good information. So the machine, the station, has to really be designed to be a gauge first and an assembly station after. Right. It has to function as a gauge, and as long as it's measuring accurately and giving good feedback to the presses.
The positioning part's very simple.
Yeah, it's a very simple thing. It's a very simple application after that. Right. It's generally when I'm talking to a customer, I normally emphasize that the key thing is designing the gauging, the way you measure the part. Design that properly and everything works. One of the other key things is that however you're measuring in station, if you have an offline gauge, you have to measure it the same way.
Right. And you have to measure it.
Correlation problems.
Generally, too, when we're taking these measurements, one of the neat features, I guess, in some of the ways we do it, some of our techniques, is we're not measuring while it's under load, because you got to remember this is being pressed in with a high amount of force. So we actually back off, take the force off of it, but the probe still maintains contact, and then we get a real measurement there. So not under load is when we take our measurements. So if you do have an offline gauge and you take to that gauge, it's generally not under load because you're not pressing anything. You're simply gauging it, and then it gives you the same reading, and then you can pass capability and gauge R&Rs and things like that. So
exactly. So that's an example of what we call measure and make and measure. We're actually measuring the critical dimensions of the part as we're assembling it with either digital or analog probes, taking that information back and using it to control the presses as we're making the parts. The first application we did like this was many years ago, and it was with a Ford engineer, and he used the phrase, it was like we're cloning parts. So we have used that term since then about cloning parts, because he was making his parts so repeatable after that. I don't have his permission. I would like to throw his name out there and give him credit for that, but I haven't asked him. So
well, that was so long ago.
It was probably okay.
Yeah, and you guys are so old.
That was when I was a kid back then. Yeah. I had hair back then.
Right.
But so that is our measuring. We use this very similar technique in pressing armatures into motors, pressing stators, pressing impellers in the pumps, and
a lot of times wherever there's some type of critical dimension you're trying to hold a tolerance to, and you generally see a lot of that on different part prints and things like that. But like Glenn said, those applications are pretty common for us, and we really pioneered that whole process. Our systems basically have, like I mentioned before, have these canned routines that are designed exactly for that.
The canned routine for the measure and make is called the measure command.
Pretty unique.
Very creative with our naming. Yeah.
Well, we're engineers, we're not marketing people.
Yeah. So the second thing we wanted to talk about today is a very similar thing. Instead it's make to a function. Instead of having a critical dimension, you have a critical function of a part. Can you make to that critical function? And that means you're getting data external from the press that is helping to control the press. But it's not dimensional data, it's some other kind of data.
Right. And a lot of times that other data is torque, it can be force. We'll talk a little bit about something simple that we can all understand, and that is just pliers. If you take typical pliers, and I have an example here, and the picture here kind of shows that, is generally there's a rivet on here, and what happens is that rivet gets crushed by using a press of some type. But how do you know how much to crush that and how much actual effort it will wind up having on the part when you try to use it or when it tries to function? So basically what Promess does in these types of applications is we'll incorporate a press to crush the rivet in some cases, and then we'll have another actuator that actually actuates the mechanism and then gives either torque or force feedback on that, so that when I go to use this, or when the customer sells it, that it's exactly the same from one to the other. It's easy to operate. but it's not too loose to where it's sloppy. So how we do that basically is we'll use multi-axis in a lot of cases with our Ultra Pro controller, and we will press and crush the rivet. And then as we're doing that, we actuate the arm with another press or a torque unit and measure the amount of torque that takes to move it. And once it gets to within a specified range, then it's done at that point. And it's
They're basically calibrating every part as it's being made.
right.
I mean, in essence, that's what we're doing. It's nobody cares what the dimension of this rivet is and where that rivet is riveted to. You could have a press and press to exactly the same height every time, but because of the way the metal flows, because of part tolerances or whatever,
Right.
you'll get different actuation forces. Really, all the people care is that it's a tight, that it's a not a sloppy fit, but it's workable.
And it's unrealistic to think you're going to machine and make precision parts for a tool that gets thrown around and used every day.
Cold heading a rivet is not that accurate either.
Right. So it's important for it to function properly in the same from one to the other and not necessarily be a really high cost to machine these parts to get them exactly the way you want them, and that doesn't even guarantee success.
And this is a real application we've done numerous times, both with just cold heading a rivet, orbit forming, or some type of roll forming of a rivet. We thought this is a nice application to talk about because everybody can relate to it. Everybody uses hand tools, but we do. There's other applications. We do exactly the same thing. Ball joints, which these control arms have, they have an articulation torque, and we'll have a torque unit rocking the ball joint, measuring that articulation torque as this is being roll formed, and we're controlling the actuation of the roll former. And as soon as when the articulation torque reaches a certain torque, we know that
to stop basically,
it's
and
done.
then it's done. Yeah.
So the ball joint is another application where we use that.
A lot of automotive components we do this with, like steering columns. In your steering column, when you make the adjustment, there's a hinge in there. It's the same idea there. There's actually 2 rivets on each side of this hinge, and I don't have that part here. But same thing. We actually crush those rivets. We do measure the rivet height on that, just because it's information they want to have, but it's not really relative to how it functions. And then we use one of our smaller presses because it's a very light force to then actuate that back and forth until it makes a good part. So a lot of times these applications we're talking about aren't just one and done either. They basically require several steps to them. So as you press and torque it and press and torque it, there's multiple.
Sometimes you have to press it and back off. Like on the pliers, we simplified it. When you're pressing, it actually clamps everything together.
Yeah.
So you got to press it to a distance, back off, check it, do it again. So it's an iterative process. Another application we did, which was really cool, I thought back in the day, was because if I can relate to it, I had an old 73 Roadrunner that every time you hit a bump, the visor would fall down.
Yeah.
The visor can't be too hard to push up, and it can't fall down when you hit a bump. So this is that's an example of controlling presses based off articulation force, and normally it's done with torque. We do it with many other sensors also, but the two relate to each other, whether you're using an actuator and measuring articulation force and or some other sensor and positioning to that, or you're using dimensional probes. It's very similar. It's just what's critical on that particular part.
Yeah, exactly.
So what we'd like to do is kind of go over our takeaways. We've mentioned these before. Main takeaways, if you get one piece of information from this little talk we're doing, and if you have applications like this and you're interested in trying to use one of these types of solutions, the main takeaway is think gauge first, whether you're gauging position, whether you're gauging torque, whatever is the critical function of the item you're working on. We've done pressure relief valves where we're measuring pressure and adjusting.
It's not just torque, position,
right,
and that type of thing. It can be pressure, it can be flow, all different types of sensing where we can incorporate that into the system and then react to it to make sure the part functions or is assembled to the correct way.
Yep.
And I think you mentioned this earlier, but I think it's good. to say it again, but and it goes along with think gauge first, is you're designing and measuring a station that assembles parts. You're designing a measuring station first that assembles parts second.
Right.
You're not designing an assembly station first that measures parts. It's important to say that because
that's a key problem. A lot of people will
right.
design the assembly station first and then tack on measurement after. They take like a station that they've always used and think about how can I tack on measurement, and it's got to be reversed.
For sure. And obviously I'm head up the application group, so we've got years of experience with this type of stuff and techniques and things we've seen over the years. So if you are interested, like Glenn had mentioned, and you have applications where you're thinking of something like this, we can offer assistance on that and some guidance on
Yeah, we have
how to
tons and tons of experience and a
Especially
lot of
you,
application.
actually. So
yeah,
I'll send them right to you.
That's fine. It's fun. I love these kind of
I know,
applications.
this is the fun stuff.
The other thing is we have at our PDC, our Process Development Center in Brighton, Michigan, customers come in all the time and we help them develop these types of applications. So we can really help you with this. And again, so the think gauge first, however you're measuring in the station, if you have an offline gauge, which you really shouldn't need now, because the third thing is that it must pass a gauge R&R. If I have a gauge online, I'm measuring as I'm making the parts and it passes a gauge R&R. Why do I need an offline station?
Right.
But if I do need an offline station, if for some reason I have to have one, the way I hold the part, the way I measure it on the in station and the offline has to be the same, because that's a problem we've run into before, is you get some correlation differences just because you're holding the part differently.
Right. And a lot of times it's just the fact that, like I mentioned earlier, it's just under load. And when you're under load, you have deflections and different things that affect it. And a lot of that error is seen there. And if it doesn't match, doesn't pass the gauge R&R.
Yep.
So that's why it's really important to make sure that matches the offline.
The measurement technique, whether it's dimensional or torque or whatever, you have to be able to measure the part. Like if I take a part out of the station, I want to remeasure it, I have to be able to put it back in the station and remeasure it. I mean, that's part of being able to do a gauge R&R. So that's a critical thing also.
For sure.
Okay. All right, now we'd like to open up the floor to questions. If anybody has any questions.
So before we do the questions, we had a connection issue. So it started like almost at the beginning of the plier talk. Can you guys cover that application just briefly again, and then we'll go into the questions?
Sure.
Yeah, sure. You want to take the pliers?
Sure. So make to a function, I guess we had some technical difficulties, so we'll talk about this again. Basically making to a function, or the plier application, you want to bring the picture up maybe that would help. So like Glenn had mentioned earlier about measure, make and measure, make. Make to a function is a little bit different. It's not necessarily using measuring probes now. Now we're using additional actuators as part of our process to be able to make the part function the way it's intended to function and function the same from one part to another. So the pliers is a good example of that. Typically you have a rivet here that puts the two halves, holds the two halves together. What we typically do is we'll have a press that'll upset the rivet or crush the rivet, either with just straight linear force, or sometimes we'll utilize some type of orbiting rivet head on the end of our press, but we basically get the force feedback from that. And then we'll have another actuator, either a torque system or a torque unit or another press that moves the handles in and out. And based off how far we crush that rivet or how much effort we put on that rivet, we can then control that and get the necessary torque that we need in order to have this function how it's supposed to. Because if it's too loose, it's going to be sloppy and customers won't like that. If it's too tight, it's not going to be workable. And so there is
I have a pair of side cutters at home like that. They're too tight to use.
So basically, that's the make to a function aspect we're talking about.
Which is in relation to, so again, you're making to a dimension or you're making to a function. From the control aspect, it's very similar.
Right.
Okay. We're ready for questions. The perils of live.
Yeah, I guess we had a little technical difficulty here. So, all right, can we control the other types of sensors? This is a two-part question. So the first one is pretty obvious. Yes, we can. We kind of covered that. We can control to force, torque, obviously,
Pressure,
any type
flow.
of distance, pressure, flow. We've even done current, things like that. So on electrical components.
Yeah, on pressure and flow, we have a really cool application that we did, basically calibrating a pressure relief valve. Every single part that was made, we calibrated it to open at 1,000 PSI or whatever the target pressure was. And if anybody's interested in that, it's kind of a long one to go through the application, how we did it, but we have pretty good application notes on it. Would be very happy to send them to you. So if you have any application where you need to assemble to a pressure or a flow, we have really good application notes on that.
Can you hold a force until a temperature is reached, for example? Yeah, that's no problem.
Yeah, we've done actually like doing bearing quenching and other types of applications like that. It's pretty common for us to actually do that. Come down and have to hold a force. And some parts, as it's heating up or cooling off, they will move around, and you want to hold a force, and so that the press is designed to move and so not hold a position while it's cooling, but actually if you program it, say 1,000 pounds, it'll move around and continue to hold 1,000 pounds as the part's expanding or contracting. So it can follow the part if need be.
Yeah, follow the part. Go ahead.
No, does your press account for deflection in a machine structure? And yeah, we have numerous techniques for handling that. One of the more simple ones is if you know the spring rate of your machine structure, and I know that it deflects 10 microns for every 1,000 pounds, the press is smart enough to compensate for that. You just have to put in the spring factor of the mechanics of the system. And it actually, there's a technique for using the press to calculate the spring factor and then using it. But another way to do that is just, if a lot of times, depending on the accuracy needed in the part, is you just build a dimensional measurement right into your fixture. And so you're taking out all of that
Right.
structure flex.
One thing to note maybe a little bit is that a lot of times, I mentioned this earlier too, is that we just take force off of it when you take the measurement, and the deflection is taken out of the equation at that point. So.
I'll let you get that one.
Sorry I came in late, and maybe you covered this, but how do you account for the flex in the part while pressing the bushing in? Well, I just mentioned that. So a lot of times what we do when we're pressing the bushing in, our measurements are taken when it's not under load. So when there's no force on it. So we have techniques that we do for that. Our measure step or measure command we talked about earlier has that built into it. But other mechanical components that help with that is maintaining contact on this side with the probe using the spring-loaded detail on the end of the press allows us to back off and still maintain contact with that probe on there. So that takes the deflection out of the equation.
Right, if you can imagine pressing these bushings in, you might have thousands of pounds on these, and so you're backing up this is not a casting, the stamping, and as you're pressing, these ears are closing in, so you get a smaller measurement, and when you take the load off them, they may open back up. So we're measuring with the load off, and we have what we call a retract step, where we press, we retract, we measure, and we re-hit. So it's an iterative process. Again, there's a couple different techniques. Sometimes that's needed, sometimes it's not. But we've done it enough to know how to solve those problems.
Yeah, maybe one thing we should mention too is about a master part. So a lot of times what we'll do is we'll either make a master part, so we'll just jog it together and make it perfect, and then weld it maybe so that it can't move. That gets put into the station, and then we come into the station with our actuators and our probes, and we call that our zero position.
Basically, zero the gauge.
Zero the gauge at that point. And then, like what Glenn said, the measure step then takes these iterations to try to achieve that zero or within a tolerance around zero. And that's kind of one of the methods or techniques we use for that.
We didn't talk about this part because, again, just for time on a cast part, but these bushings also don't have an outside can. It's only rubber. And these you have to kind of bounce into place. You hit them to a depth, you back off. You hit them short on purpose, back off, see how much you've missed, and you bounce them in. And sometimes it'll take 3 or 4 or 5 hits to kind of nudge it into place, because these are very hard to to put into place accurately.
Right.
But we've learned over the years how to do it quite well. But
Yeah, the rubber adds another component of complexity to how you measure that, but we've got to
For
figure
sure.
it out, I think. For make to a function, channel lock example, are using several different fixtures or all in one?
Usually you can, depends, it really is part dependent. Normally it's one station, but you may have a series of different fixtures to hold the different geometries of the part.
Right.
Because again, it is a gauge. I mean, this one, because we're measuring the function, it's not so critical as far as measuring microns or measuring dimensionally, but you still have to hold it properly and be able to actuate it properly, because you're exercising the part depending on how you're exercising it as you're cold heading or orbit forming the head. So yes, it really is part dependent. We do some applications where people may have just 3 models, and they'll be clever enough to make the tooling and fixturing where all 3 will fit in one.
Right.
We do other applications where people have 30 and 40 models, and they have to have different sets of tooling.
For sure. Yeah. How many LVDTs can you use? So it's really
Ultra Pro
unlimited. Yeah, with our Ultra Pro system, it's very modular, so we just add modules that basically can take in more analog and encoder inputs.
Right. The Ultra Pro system is EtherCAT based.
Yep.
So you just keep adding in, we have what we call a digital signal conditioner. So you just keep adding in digital signal conditioners, and I don't know what the EtherCAT limit is, but it's thousands.
I think actually our software group puts a limit on it, but we could have up to.
Yeah.
I think the most we've done is we've done like maybe 10, something like that.
Around there.
I'm thinking of some of the function test stuff we've done.
Yep.
I have a process which I need to control to a precise precision with a very narrow window of error. Do you offer a loaner press system to test my concept? Yeah, we sure do. That's where I'd recommend you just call Promess, ask for the application group, or if you have a particular sales guy you've used with Promess, talk with him, and we can get you set up with a system to be able to help with your concept. We can do that sometimes at your facility. We kind of have to work that out, or other times it's in our PDC. I think you talked a little bit about our product development center here in Bright, Michigan, where we already have systems set up, and with a little bit of tooling and a little bit of your help, we can generally make that work for you guys. So.
Yeah, we have, like John was saying, just to reiterate, we have a process development center in Brighton, Michigan at Promess, where we have all of our equipment, and almost on a daily basis, we have a customer in that we're helping develop processes for. If we don't have the customer in, then we are sometimes, especially during these COVID times, they'll send us the parts with instructions and maybe some tooling, and we'll set up, do all of the setup, run the parts, video it, make a report, and send it out.
Put together a data package that includes all your information, what we did, the results we got from that, and then we'll send that to you. And believe it or not, that's all free of charge. So.
Yep. So, well, for today, if you have any other questions, definitely send them to us. We're here to help. We have a very, very strong application group, as we've mentioned. Promess has been doing this kind of thing for a long time, and we're really eager to help you guys. We can help you improve your processes, make better parts, measure in station, know whether it's a good or bad part before it leaves the station. I mean, that's really what the goal should be. We're here to help you. Our phone number is 810-229-9334. Website is promessinc.com. That's all one word, PROMESSINC.com. Please email us or call us. We're here to help.
Sounds good. Thanks for your time.
Thank you.